Hi folks, we are on the Unit 1 Day 5 lesson. This is video number 1. Today's lesson is about the properties of vectors. Now some of these, lots of these probably, will likely feel to you sort of a, yeah, duh, I thought so sort of thing, but we're going to take this opportunity to think about vectors in more of an abstract mathematical way. For those of you who are continuing on into higher level math in university courses, you'll see a lot of different number sets or types of numbers and definitions of number sets that may not follow the rules that we're used to for real numbers, and that that a lot of vector operations do follow. So we're going to kind of explicitly define which properties the vector operations do follow, and kind of analyze, are these true for real numbers, and is why kind of geometrically, for the ones that we can do this with, does that work. Okay, so the first one here, we've talked about this very early on when we were talking about adding and subtracting vectors, and that's the commutative property. So we know that if you have two vectors, A and B, it does not matter what order you add those vectors in. And we saw this geometrically when we were looking at two vectors. If I took vector A, let's say there, and then added on vector B, if I did them in that order, head to tail, and then got vector A plus B, we know that that would be equivalent to if we had taken the vector B first and then added on vector A. So this is not anywhere close to being a proof, but it is hopefully kind of a visual justification that will make sense to you. Now, once we get more into working with algebraic vectors, we will be actually able to do proofs of some of these values and some of these properties. But for now, we're just going to kind of look at them in terms of the geometric vectors or a diagram and say, oh yeah, that kind of makes sense. Like that looks like it should work. But we're going to have to hold off on a more rigorous proof until we learn some of the operations with our algebraic vectors later in the unit. So that's the first thing. If you're adding two vectors, it does not matter what order you add them in. The addition is commutative with vectors. The next one is the associative property, and this is one that we proved in an earlier lesson in one specific example, looking at, I believe it was a cube or a rectangular prism. And by kind of analyzing which sides would have been equal given vectors A, B, and C that were along the outside edges of that shape. So the associative property basically means if we're adding up three vectors, it does not matter what order we add them in, these vectors will be equal no matter which two we add together first. And of course this would also be commutative, so it would be B plus C plus A, because we already know the commutative property. So you could draw this out, and we did do an example or two of where we drew this out. So if I was going to, this may get a little bit messy, but if I was going to kind of add, let's say, kind of some straightforward vectors here. If I had, for instance, A, B, and C, like that, You can do just kind of a little diagram. If we had A plus B, and kind of picture those head to tail giving us this diagonal, and then adding on our C at the end. So that's going head to tail with the A plus B. And again, not a proof, but just kind of a visualization of, does this make sense to you, why that would be true. And then if we do the opposite order, say B plus C, I'm going to try and draw this as accurately as I can because it might all fall apart here. So there's a vector B plus C. And then we want to do A plus B plus C. And then go through this, we will end up with, looks like, an equivalent vector there. So we can kind of draw a little diagram. We can work this out. We could, of course, be a lot more accurate in our sketches than this, and we could prove it for some particular cases doing actual calculations. But once again, this is something that's going to have to wait for rigorous proof until we get to operations with algebraic vectors and are able to convert these into a more workable form that we can prove this using the properties of real numbers that we know. Okay. This one is the distributive property for scalars. So if you take the sum of two vectors and multiply that by a scalar, it's equivalent to multiplying each of those two by a scalar. So I'm going to kind of say, if we have A and B, and we get a resultant vector here of A plus B, if we multiplied each of these two by a scalar, this one's a little bit easier to see and kind of justify a geometric proof. Let's call this K times vector A. There's some more cases to think about depending if, say, that scalar value is positive or negative. But we can kind of justify this one with similar triangles, can't we? That we would know that these would have the same angles between them, and that the ratio of these sides are actually equal because each of these kind of corresponding sides has been multiplied by the same real number. So these form similar triangles. So that this would be K times vector A plus B based on the same scalar multiple of that length. So it's a little bit more of an accurate proof. It's not quite an exact proof, but hopefully kind of seeing the relationship of similar triangles there is a little bit convincing. Here, if we're multiplying, remember that multiplying by a scalar, we can multiply by one scalar and then another scalar. So say you like doubled the length of A if n was 2, and then we tripled that. So we would have gone from A to 2A and then triple that to 6A. That's the same as multiplying those two scalars together and then multiplying by A, or multiplying A by the product of those. So it does not matter what order you're multiplying in, and I don't know how I would really draw this one. It's not an addition one. But basically, these scalars don't matter. You could switch the m and the n around too. It does not matter what order you multiply scalars in. Any multiple of those scalars will just be the same vector multiplied by the total product of that. Okay. This also, if we have, say, vector A there, and we have one multiple of A in that direction, and another multiple of A and we were adding these two vectors together. If we're adding collinear vectors, and this would be m times A plus n times A, which you are just adding up the total magnitude of each one multiplied by the original magnitude of A. And again, not really a proof, but just more of a visualization. So that is all of the different rules that we're going to use. And it seems a little bit overwhelming, I think, when you guys are first looking at these and thinking, do I have to memorize them? Really, it's just kind of proving to you that we can do operations on vectors much the same as we can on regular real numbers and regular variables that we would be dealing with. Not everything is going to work the same. Like I mentioned before, we are not going to look at multiplication of vectors together or division of vectors. That's not really an operation that's defined. But when we're looking at kind of a coefficient, like a scalar multiple, and something in terms of like collecting like terms on vectors, with that the distributive law, that last one, that really it is like, this is a form of collecting like terms. If you have, say, 3a plus 2a, that's 5a. So that's going to come really in handy when we want to simplify operations with vectors. So in this case, we're going to be simplifying this, that this multiple here is going to be 15 times vector x plus 6 times vector y plus 3 times vector z. And then we can take this, that this is the negative of each one of these vectors. So minus vector x minus 3 times vector y, and then minus a negative vector. Negative of a negative is positive. So usually at this point people say, oh, it's just like grade 9 collecting like terms, except I have to remember negative or vector signs on top. And yeah, that's it. So we get 14 times vector x plus 3 times vector y plus 4 times vector z. So just kind of a demonstration that we can keep to our regular kind of standard algebra work using vectors, other than, again, we cannot multiply vectors together. That's not something we can do. But multiplying by scalars, collecting like terms, it all works just like if those are regular real numbers. Okay, so here we've got vector x is 3 times vector I plus 4 times vector j. And some people bring this up. When you have i's and j's, typically in the kind of math editing, it doesn't put like a dot on your I or your j, just because I think like the vector sign on top kind of gets in the way. It's not incorrect to do that. If you write an I and put the dot and then put the vector sign above, that's totally fine. But most of the time, math textbooks or math editing software on Word or Google Docs will remove that dot. Actually, I think Word removes the dot above the I or the J, but Google Docs does not. So there's no actual reasoning for it. I think it's just to kind of make the typesetting a little bit more clear. So here, and y is 2 times vector I minus j. So if we want to find expression for vector x minus y, we just take vector x, so 3 times I plus 4j minus 2I minus j. And then we're going to do the same thing, just simplifying 3I. I don't know, I guess I'm kind of going both ways on those dots. 2I plus j. And then we get a summary. I think I'm going off the screen a bit here. So we would have 1 vector I plus 5j. And that would be an expression for x minus y. One last example here. Same vectors, x and y. And we want to figure out what would vector I and vector j be in terms of x and y. So if you wanted to kind of isolate, and this is going to be very similar to like a maybe grade 10 question when you were doing substitution and elimination, we want to kind of solve for I and j. Now, I think that this is probably the easiest one to get started with. So if I have vector y is 2 times I minus j, I can rearrange this and say j equals 2I minus y. And then I can rearrange kind of both of these and get solve for I. So I'm going to sub this one, this j, in up here. So x equals 3I plus 4j. I'm going to substitute in this value for j. So vector x equals 3 times I plus 4 times 2I minus y. So x equals 3I plus 8I minus 4y. And it's a little bit messy to remember all of those vector signs, but it is important. So isolating here for I equals, I get x plus 4y equals 11I. So I equals x plus 4y over 11, and we could change that to a coefficient of 1 over 11. We, again, don't really have division with vectors, but we do have multiplying by a reciprocal. So I'm multiplying that by 1 over 11. And then to figure out what j would be, we'll sub this back in up there. So j is 2I minus y, and I'm just going to sub in my expression for I in here. So 2 times x plus 4y over 11 minus y, and just some kind of simplifying and common denominatoring. I don't know if that's a word. 2x over 11, and then I'll have plus 8y over 11, and I'll make that 11y over 11 so that I can simplify this. 2x over 11 minus 3y over 11. Okay, so we've been able to rewrite vectors, and you can rearrange equations for vectors basically like you would rearrange equations for variables involving real numbers, using many of these kind of same techniques. So this day is just to kind of show you that you are allowed to do